Okay, let's unpack this. Imagine a cosmic detective story unfolding over light years, where the clues are faint, rhythmic pulses from, well, unfathomably distant objects.
And the main characters are the burnt-out remnants of stars.
Exactly. Today, we're taking a deep dive into this fascinating, newly discovered class of white dwarf pulsars. You've shared some truly incredible research, especially digging into the Gaia mission data.
It's really pushed things forward.
So our mission today is to really extract the most important nuggets of knowledge. We're going to explore what these enigmatic objects are, how they kind of defy our previous understanding of stellar evolution,
They certainly do that.
and the surprising new theories emerging to explain how they even exist. Get ready for some serious aha moments, I think.
It's a truly remarkable area of astrophysics right now because it's pushing the very boundaries of what we thought we knew about stellar end states. And Gaia's contribution, like you said, has been absolutely pivotal.
Right. But okay, before we plunge into the pulsing mysteries, let's just quickly set the stage. For anyone who might need a quick refresher, what exactly are white dwarfs?
Good question. Think of white dwarfs as the evolutionary end product for most stars. Pretty much anything less than about 8 times the mass of our own sun.
Oh, okay.
Once these stars exhaust their nuclear fuel, they shed their outer layers, leaving behind this super dense core, about the size of Earth, but with maybe half the sun's mass crammed in there.
So they're not actively burning anymore like a main sequence star. How do they manage to radiate energy then? I mean, we see them.
That's a key point. An isolated white dwarf just cools down. It happens over incredibly long time scales. We're talking many multiples of the age of the universe, in fact.
Wow.
They're slowly radiating away their residual thermal energy. You see them emitting from the ultraviolet all the way to the near infrared, effectively like uh, cosmic embers slowly
Yeah.
fading out.
Cosmic embers. I like that. But they also play a pretty significant role in binary systems, don't they? They're not always alone.
Oh, absolutely. In fact, they're the dominant form of compact object binaries. We see them everywhere once we look closely.
Right.
And in what we call cataclysmic variables, or CVs for short, you've got a white dwarf in a very close orbit with a normal main sequence star.
Okay, a close orbit. What happens then?
Well, the white dwarf's strong gravity can actually strip material from its companion. It's a process called Roche-Lobe overflow.
Roche-Lobe overflow. Sounds dramatic.
It is. Essentially, the white dwarf pulls gas directly off its companion star, and this gas usually forms a swirling accretion disk around the white dwarf.
Ah, the classic accretion disk.
Exactly. And this mass transfer process, this disk, it gets incredibly hot. It leads to atomic line emission, X-ray emission, and if the white dwarf happens to be magnetic, that radiation can even extend into the near and mid-infrared.
Okay, so that sets the scene. We have these dense stellar remnants, sometimes quiet, sometimes interacting dramatically with a companion. Now let's get to the central enigma of our cosmic detective story. The discovery that really shook things up, AR Scorpii, or AR Sco. This wasn't always known as a white dwarf pulsar, was it?
No, not at all. Far from it. Since the early 1970s, AR-SCO had been classified as just a common periodic variable star, specifically a delta Scuti type.
Which is just a type of pulsating star, right? Nothing too out of the ordinary.
Exactly. A kind of slightly unstable single star. That's what made the 2016 breakthrough so, well, astonishing.
Right, this is where it gets really interesting. Martian colleagues found it wasn't a single star at all.
Nope. It was a close binary system, a white dwarf with an M-star companion, a small, cool red dwarf orbiting each other every 3.56 hours.
Pretty tight orbit. And relatively close to us, too.
Yeah, just 116 parsecs away. Astronomically speaking, that's practically next door. But the mind-blowing part, the real shock, was the pulsations.
Okay, tell us about those.
It was found to be pulsing in brightness every 118 seconds. Now compare that to the 3.56-hour orbital period. This was much, much shorter.
118 seconds versus hours. Yeah, that's a huge difference.
And these were incredibly intense optical pulses. The brightness increased by a factor of 4 within just 30 seconds.
No.
And really unusually for cataclysmic variables, these pulses were also detected at radio frequencies. That was another big surprise.
So what was the initial interpretation? What could cause that rapid pulsing?
The conclusion from Marsh and the team was that these optical pulses reflected the spin of a magnetic white dwarf. And they even observed it slowing down, spinning down on a time scale of about 10 million years.
Okay, spinning down like a pulsar, but a white dwarf.
Exactly. But what's even more fascinating, digging deeper, is that the pulsations actually comprise 2 very similar frequencies. Slightly different.
Two frequencies. How does that work?
Well, the higher frequency component at 117 seconds, that was associated with the white dwarf's direct spin period. Makes sense. But the stronger, lower frequency component, the 118-second one that dominates, that turned out to be a reprocessed or beat frequency between the spin and the orbit.
A beat frequency. So, wait, what does that mean for where the light is coming from?
It means that while the white dwarf's spin is the ultimate engine driving the pulsations, the light pulses themselves mainly originate from the cool companion star. The M dwarf is being illuminated or somehow energized by the white dwarf's beamed output.
That's why. So the white dwarf is the lighthouse beam, but we're seeing the light hitting the nearby ship, the companion star, and flashing.
That's a pretty good analogy, yeah. It's quite a twist. It fundamentally challenges our assumption that the main emission source in these systems is always the compact object itself.
And this led to its groundbreaking classification as a white dwarf pulsar. And you mentioned its spectrum looked like synchrotron radiation.
That's right. Its broadband spectrum is characteristic of synchrotron radiation. For listeners, that's the specific type of light you get when super-fast relativistic electrons spiral around magnetic field lines.
Which implies strong magnetic fields and high-energy particles. Though you said the source of those electrons is still a bit uncertain.
Still a bit of a puzzle, yes. How they get accelerated to those energies in this specific system is an active area of research.
Now, this leads us to a fascinating historical note you mentioned. The idea of a white dwarf pulsar wasn't entirely out of the blue.
No, amazingly, someone had kind of predicted this. A researcher named Iksanov, way back in 1998, had already suggested that another closed binary, AE Ayer-Kier, was effectively a white dwarf pulsar.
Even without seeing these kinds of rapid pulsations? How?
He inferred it indirectly. He calculated that the compact object's spin-down power, the energy it was losing just from slowing its rotation, seemed to exceed the system's total observed luminosity from accretion and the stars themselves.
Ah, so there was missing energy, and he figured it must be going into something like pulsar beams.
Exactly. It implied some kind of pulsar-like mechanism of particle acceleration, powered by the white dwarf's rotation. Even though the pulses weren't directly seen in AER here at that time, he was predicting a whole class of objects.
That's truly prescient. Have other candidates popped up since Sco?
Yes, since Sco's discovery, at least 3 other systems have been suggested as potential white dwarf pulsars by researchers like Kato and Kochiguchi. There was even a transient discovered by Gaia, Gaia-22ij, that was proposed as one.
Right.
But, and this is important, none of these others have actually been confirmed yet. They show some suggestive properties, but we haven't definitively seen the same kind of behavior as Sco, or the next one we'll talk about.
Okay. So for a while, Sco was this singular anomaly, a bit of a cosmic unicorn. The big question then became, was it truly unique, or were there more hiding out there?
Exactly. Was it a one-off freak, or the first example of a whole new population? And the answer came relatively recently with the second confirmed white dwarf pulsar, J1912 4410.
And this wasn't just luck, right? They were actively looking.
Correct. This was a targeted search. Pellisoli and colleagues specifically hunted for objects that looked like Sco. They used criteria like non-thermal infrared colors, variability, and importantly, their location in the Gaia color magnitude diagram. They were filtering the huge Gaia dataset.
Smart. Using Sco as a template. And what did they find with J1912?
They hit it. High-speed photometry, basically taking very rapid pictures, revealed strong pulses again, this time with a 5.3-minute period.
Longer than Sco's, but still very short compared to typical binary periods.
Definitely. And again, the optical flux increased significantly during the pulses by up to a factor of 4. It was also picked up as an X-ray source by the Rosetta telescope, and Gaia data itself had flagged it as a likely compact binary candidate.
This really highlights Gaia's role again, doesn't it? How specifically did Gaia help nail down the details for J1912?
Oh, massively. The Gaia EDR3 distance measurement was absolutely crucial. They measured it to be 237 parsecs away, plus or minus only 5 parsecs. Incredible precision.
And knowing the distance lets you figure out sizes and brightnesses accurately.
Precisely. That distance allowed the researchers to constrain the M-dwarf companion's radius by fitting its spectrum. And once you have the radius and the orbit, you can start estimating the masses.
What did they find for the masses?
They estimated about 1.2 solar masses for the white dwarf, quite hefty, and about 0.25 solar masses for the M-dwarf companion. And intriguingly, the companion star was found to be nearly filling its Roche lobe, over 90% full.
So it's right on the brink of spilling material onto the white dwarf again, or perhaps it already is, intermittently.
That's the implication, yes. It's very close to interaction.
And what about the energy budget? Was there that same luminosity puzzle as with AR-SCO?
Yes, very much so.
Yeah.
Maybe even more pronounced. When they combined the measured spectral energy distribution, all the light across different wavelengths with that precise Gaia distance, they calculated a total bolometric luminosity of about 9×226 joules per second.
And how does that compare to what the stars themselves should produce?
It blows it out of the water. The expected total stellar luminosity, just from the white dwarf cooling and the M dwarf shining, is only about 1024 joules per second, a factor of 100 lower.
Wow, so that extra energy, like in AR-SCO, must be coming from somewhere else, either faster spin down or maybe some low-level accretion.
Exactly. This suggests either a more rapid spin-down rate compared to AR-SCO or perhaps another energy source is contributing, like residual or intermittent accretion.
Okay, so let's try and tie this together. We now have two confirmed white dwarf pulsars, AR-SCO and J1912. Both show these energetic pulses, seemingly powered by the white dwarf spinning down. But you mentioned a major cosmic paradox earlier. What is it?
The paradox is this. Okay, the measured spin-down rate of these white dwarfs does seem to provide enough energy to power the pulses we see. That part checks out.
Right.
But reconciling that rapid spin-down rate with the fact that the white dwarf is spinning so fast in the first place, that's the significant challenge.
Why is that such a challenge?
Because think about how stars evolve. Non-interacting main sequence stars, like our sun, they actually slow down their rotation as they age due to magnetic braking, losing angular momentum.
Okay.
So when they finally become white dwarfs, we expect those remnants to be rotating relatively slowly. We typically measure white dwarf spin periods in days, not minutes or seconds.
Ah, I see. So to get something spinning every few minutes, like J1912, or every couple of minutes, like AR-SCO, it must have been spun up somehow.
Exactly. The observed rapid spin demands a prior spin-up phase, and the most likely way to do that is through mass accretion from the companion star in the past. The infalling material carries angular momentum, spinning the white dwarf up like a flywheel.
Okay, so maybe they were spun up by accretion earlier in their lives. That makes sense. But then there's the magnetic field conundrum you mentioned.
Yes. Now, we do see white dwarfs in regular cataclysmic variables that have rotation periods comparable to AR-SCO's 117 seconds. And we explain that by exactly this mechanism. Angular momentum gained from accretion.
So far, so good.
But AR-SCO's observed spin-down rate implies it has a really strong magnetic field providing the torque to slow it down. We're talking 5,000 to 10,000 Tesla. That's huge.
Yeah.
And here's the rub. If you try to spin up a white dwarf to those speeds via standard Rochlot overflow accretion, the physics suggest that the magnetic field would actually interfere with the accretion process if it were that strong. To get it spinning that fast, the magnetic field would likely need to be much weaker, maybe around 100 Tesla.
So the strong field needed to explain the spin down seems incompatible with the conditions needed for the initial spin up.
That's the big disconnect. It's a fundamental problem. How do you get this rapidly spinning and highly magnetic white dwarf? Standard models struggle to produce both simultaneously. It's like the evidence points in two different directions.
A proper cosmic head scratcher. So we have these rapidly spinning, highly magnetic white dwarfs, but the standard story of how they got that way doesn't quite add up. Is there a proposed solution, some way out of this puzzle?
Fortunately, yes. An elegant solution has been proposed, specifically for AR-SCO initially by Schreiber and colleagues. It tries to bridge this gap.
Okay, I'm intrigued. How does their model work?
The key idea is that the white dwarf wasn't strongly magnetic to begin with.
Ah, okay, so it starts out non-magnetic or weakly magnetic.
Exactly. This allows it to undergo a normal phase of accretion-driven spin-up from its companion star, reaching those very short rotation periods without the interference of a super strong field.
Okay, so it gets spun up first. Then what happens? Where does the strong field come from?
The crucial turning point, the model suggests, happens later, as the white dwarf cools down. Eventually, its core begins to crystallize.
Crystallize, like solidify.
Sort of, yes. The carbon and oxygen plasma forms a crystalline lattice structure in the core. And this is a phenomenon, by the way, that Gaia data actually helped observationally identify in populations of white dwarfs. You can see a pileup of stars at certain colors and brightnesses where crystallization slows down their cooling.
Fascinating. So the core crystallizes. And then?
Well, Theoretical models suggest that this crystallization process, combined with the strong density differences inside the white dwarf in convection, creates the perfect conditions for a dynamo.
A dynamo, like the Earth's core, generates our magnetic field.
Exactly the same principle. The movement of conductive material within the crystallizing rotating core starts generating a powerful magnetic field from within.
So the magnetic field isn't primordial, it's generated later by the white dwarf's own internal evolution. That's a really neat idea.
It is. And the model proposes that once this dynamo-generated magnetic field becomes strong enough,
Things change.
dramatically, the now strong magnetic field interacts powerfully with the companion star and any remaining surrounding material. This leads to a rapid transfer of the white dwarf's spin angular momentum out into the orbit, effectively acting like a brake.
Okay.
This braking can be so effective that it actually causes the binary system to temporarily detach, the stars move slightly further apart, and mass transfer stops.
Ah. And that explains why Sco is currently detached, not actively accreting.
Precisely. It leads to this rare evolutionary phase system like Sco, a rapidly spinning, now highly magnetic white dwarf that isn't actively feeding anymore. It's just spinning down and powering those pulses.
That's very clever, but you said temporarily detached. Does it come back into contact?
The model suggests yes. After maybe a few million years in this detached pulsar-like phase, the combined effects of reduced magnetic braking, as the spin slows, and gravitational wave emission will slowly shrink the orbit again. Eventually, the system comes back into contact.
And what does it become then?
It becomes a rapidly rotating, highly magnetic, accreting white dwarf, what we call a magnetic cataclysmic variable, or specifically, an intermediate polar.
So this model isn't just explaining Sco. It's potentially explaining the origin of a whole class of magnetic CVs.
That's the really powerful implication. It potentially solves a long-standing puzzle in the study of white dwarf binaries.
Which puzzle is that?
It's the weird discrepancy in the fraction of magnetic white dwarfs we see in different types of binaries. Observers noticed that strongly magnetic white dwarfs seem to be largely absent in detached white dwarf binaries, where there's no active accretion.
Okay.
But paradoxically, more than a third of white dwarfs in accreting systems, the CVs, are strongly magnetic. How can they be common in one type, but rare in the seemingly related precursor stage?
Yeah, that sounds like a contradiction. How does the dynamo model fix it?
It explains it beautifully. The magnetic accreting white dwarfs, the common ones in CVs, are typically old systems. They're cool enough for their cores to have crystallized, triggering the dynamo, and they were spun up to short periods by accretion before the fields got really strong, which intensifies that dynamo effect. The detached magnetic ones are rare because that phase, like Sco, is relatively short-lived.
Wow. So the magnetism appears late in the game, driven by crystallization and rotation, primarily in systems that have already undergone significant spin-up via accretion. That ties it all together.
It really does seem to. This rotation and crystallization-driven dynamo model implies that binary white dwarf pulsars like Sco are a necessary, though possibly brief, evolutionary stage en route to becoming magnetic cataclysmic variables.
And given that Sco is relatively close, only 117 parsecs.
It suggests there should be more of these out there, waiting to be found in deeper surveys, like the ones Gaia enables. And Sco spin-down rate suggests this phase can last for several million years, long enough to catch a decent number of them.
What does the model predict we should look for? What are the characteristics of these Sco-like systems?
The model predicts that the white dwarfs in these systems should be relatively cool enough to have started crystallizing. Their companions should be close to filling their Roche lobes, like we saw with J1912, and the orbital periods should typically be in the range of 3 to 5 hours.
Which brings us right back to J1912 4T410, the second confirmed one. How well does it fit?
It fits remarkably well. Pellisoli and colleagues, the discovery team, explicitly concluded that J1912 strongly supports this rotation and crystallization-driven dynamo model as the origin story for magnetic cataclysmic variables. It ticks all the boxes predicted by the theory.
That's fantastic. Finding that second example really solidifies the picture, doesn't it? It gives us a powerful new framework.
It really does. It turns Sco from an anomaly into a type specimen.
Okay, this is truly groundbreaking stuff, but
Right.
let's talk about the name. White dwarf pulsar. Is it actually the right term? Is there a bit of a semantic debate here?
There is, and it's a fair point to raise. Some researchers, notably Katz, argue that systems like Sco don't really display the core properties of a true pulsar in the way we think about neutron star pulsars.
How so? What's missing?
Well, Katz argues Sco lacks highly coherent optical or radio emission. The timing isn't as stable or precise as a neutron star pulsar clock. And crucially, the physical emission mechanism, this illumination of the companion star, is very different from the magnetospheric emission we believe happens in neutron star pulsars.
So it pulses, but maybe not like a pulsar. It's a different beast using a similar name.
That's the argument, yes. The underlying physics is quite distinct.
So if Sco isn't a true white dwarf pulsar in Katz's view, does he propose an alternative candidate? Is there something else that might fit the bill better?
Interestingly, yes. Katz suggests that a different object, a low-frequency radio source called GREAM X J1627559.5523504.3, might actually be a genuine white dwarf pulsar.
Oh, what's special about that one?
It has an inferred moment of inertia, orders of magnitude greater than a neutron star's, consistent with a white dwarf.
Yeah.
And it has a very long spin period of 18.18 minutes, hundreds of times longer than confirmed radio pulsars, but may be plausible for an isolated magnetic white dwarf spinning down.
An 18-minute pulsar, that would be something else entirely.
It would. Though it's worth noting this is still debated, and other models exist with different predictions for what the optical counterpart to this radio source should look like if it's seen. It's not confirmed yet.
So the jury's still out on that one, and perhaps even on the best terminology for Sco and J1912.
Semantics aside, yeah.
So what does this all mean then? Whether we call them pulsars or something else, these new binary white dwarf systems are clearly fascinating, aren't they?
Absolutely. They are challenging our long-held assumptions about how stars evolve, especially in binaries, and how magnetic fields get generated in these really extreme environments.
It opens up whole new avenues for understanding stellar physics. And here's maybe a final thought for you, our listener, to mull over. As Gaia continues its mission, mapping the cosmos with this unparalleled precision, it's undoubtedly going to help us find and characterize many more of these intriguing objects.
No doubt about it.
So the question is, what other cosmic classifications, what other seemingly settled categories of stars or systems might we have to completely rethink as we get more and better data? What other surprises are hiding in plain sight?